stage pipeline. So, this is another advanced version over that 6 stage pipeline. So, this is available in the ARM 11 core. So, there are two new features have been introduced. First one is the shift operation. So, shift operation, it has been separated into a separate pipeline stage. So, you remember that in the ARM architecture we have shown that before the ALU there is a barrel shifter. So, we can always do the shift operation in a separate pipeline stage. Okay. So, that way, so that has been exploited in ARM 11 architecture. So, it is a 8 stage pipeline. So, the shift operation is constituting one stage. So, if you have got instruction like this, so where we are if we have got instruction like say x equal to x plus y left shifted by 2. So, while doing this operation, this y left shifted by 2. So, this is done by a separate pipeline stage and this addition is done by a separate pipeline stage. Previously, so this was these two were done together. So, that way it was taking more time. Now, it is divided into two pipeline stages. So, the operation will be faster. Okay. So, that way it helps in the pipelining, this reducing the speed of reducing the delay of operation, and both instruction and data access are distributed into two pipeline stages. So, the fetch part, so that is also divided into two stages. So, we had the 6 stage, so pipeline. From there we have got a new stage of shift. So, that makes us 7. Then this instruction and data, they are divided into two pipeline stages. So, that is 7 plus 2 9 pipeline stage, and this execution unit is split into 3 pipelines, and they can operate concurrently and commit instructions out of order also. So, what do we mean by that? Let us try to understand. So, suppose we have a situation like this, that we have got an instruction like say R 1 equal to R 1 plus R 2 and another instruction R 3 equal to R 4 multiplied by R 5. Now, if you look into these two instructions, then this instruction, it does not affect the execution of this. So, these instructions are independent of each other. So, in that way, if you write a program in some high level language, suppose this is the program that you have written, then you can find out in this program several parts of the program that are not dependent on each other. Or if you are this is particularly true when you have got a loop body, like say I am writing a loop for I equal to 1 to 100, some statements are there. So, if you analyze this loop body, you may find that many of these instructions, they are not dependent on each other and they can be done parallelly. So, if you have got multiple execution units available, then you can that is you have got multiple ALUs available, then you can do all these operations parallelly. Though for a human being, it is difficult to find out where can we find this type of parallelism, but this is done by the compilers. So, they will find out like what are the points, what are the instructions that can be executed parallelly. So, they are actually distributed into a number of functional modules and they are done parallelly. So, this way we can have this execution divided into 3 pipeline stages, and then we can have this thing the instructions can commit out of order. Also means it is not mandatory that in the program the instructions 1 comes before instruction 2, but in the actual execution instruction 2 may be completed before instruction 1. So, if there is no dependency between the two instructions, so it does not make any difference. So, they can be completed out of order also. So, next we will see the 8 stage pipeline, that is the 8 stage pipeline we have seen. That completes the pipeline discussion. Next we will look into the instruction set architecture for the RISC processor. So, instruction set architecture means the instructions that are available in that for that processor, and also the registers that are available. So, like that. So, as we have already seen that this ARM is a RISC architecture, it is a typical RISC architecture with several enhancements to improve the performance further. So, what are the RISC features it has? So, as we have noted earlier that the instructions are similar in terms of size and execution time, and also these RISC processors, they have got large number of registers in them. So, if you look into this ARM processor, then here also we have got large uniform register file. So, this particular term file register file is this register file. So, if you so you know that the term file is the term file means it is a collection of records, it is a collection of records. So, if you look into any data structure book, so it is collection of records. But in case of processors, so we the same thing happens, like each register can be considered to be a record, and we have got a collection of such registers. So, they are often called register file. Okay. So, this is a standard terminology in computer architecture. So, this register file, it has got 16 general purpose registers, there are 16 such registers. So, that is quite big. So, each register is 32 bit and all that. Then it is something called a load store architecture. Okay. So, load store architecture means the instructions that process data operate only on registers that separate from instructions that access memory. So, we will explain this, like say architecture, what we have seen so far, like say 8085, 8051 etc. So, they are called accumulator based architecture. They are called accumulator based architecture. So, why? Because if you do any operation, one of the operand is always that special register accumulator, and the destination is also that special register accumulator. So, we always have instructions like say add a comma b, okay, or you can have say add a comma h. So, like that. So, but this first one of the operands is always the a register, the accumulator. In 8051 also we have seen that they are accumulator. So, and whenever you are accessing the memory, so you see that there it is we can mention the address and then it can do the operation, and also we also have got this type of instructions like add a comma m, and we said that the for 8085 the meaning of this instruction was a will get a plus memory location pointed to by the HL pair. So, this was the meaning. Okay. So, you see that you can also add this accumulator with some memory location. In contrast, so this load store architecture that we have, so this load store architecture tells that we cannot have this arithmetic instructions to use this memory, like you cannot have this type of add say R1 comma m. So, this type of instructions are not possible. For accessing memory, we have got specific instructions load and store. So, load and store. So, these are two instructions that are available. By load instruction, you can load some register with the content of some memory location, and store, you can store the content of a register onto a memory location. So, but you cannot use this memory operand in the arithmetic and logic instructions. So, that is not possible. So, this type of architecture, so they are called load store architectures. So, so what happens is that if I am following a load store architecture, then whenever I am doing an operation, say addition operation, then the operands must be some registers. So, maybe R1, R2, R3, which may mean that R1 gets the content of R2 plus R3. So, this may be the meaning. But so before that I have to somehow load this R2 and R3 by proper values. It may be coming from memory, and that way you have to use load instruction for that, or the immediate operands are also possible. So, so immediate part is not shown here, but immediates are also possible. So, this way we can have this architecture classified as load store architecture. So, this ARM processor they are following this load store architecture. So, instructions that process data operate only on registers and are separate from instructions that access memory. Then addressing modes are simple. Okay. So, there are various addressing modes that are available in different processors like registered indirect. So, we have in 8051 and 8085 we have seen that registered indirect mode, but if you look into later versions of processors like I-86 onwards, then you will find that there are complex mode like based addressing, then indexed addressing, then indexed addressing with post increment, pre decrement, like that there are many such variants of the addressing modes. And again the same thing, like when the architecture designers they thought about the features of the processor, they thought that all these things will be helpful, but when it comes to the compilation of programs, only a limited number of addressing modes are actually used by the designers, by the compiler designers. So, as a result there is no point supporting those complex instruction modes and addressing modes. So, in RISC architecture, so they are made simple. So, it is simple addressing mode. Uniform and fixed length instruction field. So, all the instructions they are more or less fixed, their lengths are fixed and their structure is also fixed. All ARM instructions are 32-bit long and most of them have a regular 3 operand encoding. So, all instructions are 32-bit and all instructions are 3 operand instructions. So, this is another point to note. So, we can have instructions like say add R1, R2, R3. So, there I have to have the operand 1, operand 2 and destination. So, the 3 operands are there. On the other hand, in 8085 or 8051, so you have got the instructions like add A comma B. So, that is there this A is, so this first one is the source as well as the destination and the second one is the second operand. So, these type of instructions, so they are called 2 operand instruction, they are called 2 operand instruction. Now, this type of instruction they will be called 3 operand instructions, and you can also have 0 operand instruction like say NOP instruction is 0 operand, no operand is there. So, you can have 1 operand instruction like say push. So, if you look into the push instruction, push PSW. So, this is a single operand. So, you have got single operand instruction. That way we have got different number of operands, but in ARM processor, so most of the instructions they are 3 operand in nature. So, it will have the 3 operand encoding. So, next we will look into some improved features. So, those are the basic features that are there, but there are many improved features also for ARM. Like each instruction controls the ALU and shifter and making the instructions more powerful. So, each instruction means normally the arithmetic logic instructions, so they will be utilizing this ALU and shifter modules, but in case of ARM processor we will find that this every instruction will be able to use this ALU and shifter. That way instructions can become a bit complex. So, this is a diversion from RISC architecture where these instructions are supposed to be simple, but now we are going towards a bit complex instructions. So, this ARM processor is a mix of this RISC and CISC architectural features. So, we will see that. Then auto increment and auto decrement addressing modes are supported. So, auto increment addressing mode means that you have got so I can have say add R1 comma R2 comma R3, and then we can say that this R1 plus plus sort of thing. So, that will mean that this R1 value will be added. So, R3 will become say R1 plus R2, after that R1 will be incremented as well. So, this is another job that is done. So, this is very much useful, particularly whenever you are writing code to access an array. So, array is normally stored in a memory like this. So, there is the initial address is there, suppose the array is stored in this region of memory. So, initially you set your index here, the first location, then after this one has been accessed. So, you want that the index should automatically increase. So, if that is automatically done, then we do not have to spend another instruction for incrementing this index part. Okay. That is why this auto increment is a very useful mode for this processor designers. So, this though it is not a RISC feature, because now we are making the addressing mode complex. Okay. So, it is not a RISC feature, but this ARM processors, it will have these auto increment feature. Similarly, auto decrement feature is also there with the ARM processor. Another diversion is multiple load store instructions that allow load store up to 16 registers at once. So, multiple load store the feature is like this. So, this is basically a CISC feature. So, this multiple load store is a CISC feature. So, if you look into Intel 8086 family of architecture, then you will find that there is a special instruction which is called moves, okay, moves B, moves W, moves word, like that, basically the moves. So, what it does is that if you have got say suppose this is my memory and there I have got some chunk of data in some source. So, this is the source, in the source location, a source chunk, and from there I want to move that chunk to this, I want to copy it to the destination. Okay. Fine. So, what you can do, you can set the source index register to point to this one and the destination index register to point to the destination. There are special registers SI and DI for source index and destination index, and you can have in another register CX how many bytes you want to transfer. And then after setting this SI register, like move SI comma that source address, move DI comma destination address, and move CX comma count, CX comma count. So, you can just say moves B for doing this movement. Okay. Now, this is a very useful instruction. You see that so this is in this case what has happened is that these boxes or the blocks, they are not overlapping. So, I can copy from the first location and continue till the CX number of bytes have been copied. But consider the situation where in the memory my source block is say somewhere here. So, this is my source block and my destination is like this. My destination block is something like this. So, the dotted part is the destination. Now, you see that while doing the copy, I should not copy from the beginning, because if I copy from the beginning, then this content will be lost. So, I should copy from the last location onwards. So, I should do it like this. I should do it like this. Or if the overlapping is in the other way, so this is the source and this is your destination. This is the destination. Then I should do the other way. So, I should start copying from the beginning and do it in this fashion. So, all these are taken care of by the processor. And how many cycles will it take for execution? That depends on the count value. So, that is the block size, how many bytes are there in that block. So, it will be dependent on that. So, this is a pure CISC feature because the whole operation is very complex, but at the same time this is a very useful feature, because many a time in the program, so we would like to move the content of one memory chunk to another. Okay. That way we will be very often requiring this type of operation. So, this has been taken into consideration by these ARM designers, and they have brought back this multiple load store instruction, but not in the same form as we have in this as we are having in say a Intel family of processors, but it is in a different way, but you can we can have this multiple load store. Then the next important thing that we have is the conditional execution of instructions. So, instructions will be executed conditionally. So, there is a 4-bit condition code before every instruction, and if that condition code is satisfied, then only the instruction will be executed, otherwise the instruction will not be executed. And this has the advantage of eliminating small branches and thus pipeline stalls. So, let us see how this thing happens. So, suppose we are having one if then else statement like this in some high level language. So, if R1 is greater than R2, then R3 gets R4 plus R5, else R3 gets R4 minus R5. Suppose in some high level language we have got this type of code. Now, if you consider the architectures that we are familiar with so far 8085 or 8051. So, the conversion will be, the machine code translation will be something like this: compare R1 comma R2, then jump on less or equal to L1, and then it will be here I will be doing that addition operation, add R3, R4, R5, meaning that R3 gets the sum of R4 and R5. Then there should be a jump, there should be a jump to this jump for this to skip over the next instruction. It should be a jump to L2, and then here I should have this label L1, and there I should do the operation subtract R3, R4, R5, and this is my label L2. So, this is the code. Now, you think about executing this code in a pipelined fashion. So, even if I have got a fetch, decode, execute pipeline, fetch, decode, execute pipeline in which I am executing it. So, when this instruction is executed, so when this instruction is being executed, so the next instruction will be fetched. But you see that until and unless this instruction's execution is over, I do not know whether the next instruction is this one or the next instruction is this one. So, I really cannot fetch. Okay. So, the pipeline has to wait till the execution of this JLE L1 instruction is over, and then only I will know what is the destination, and then only the fetch operation can continue. So, there is a pipeline stall. For unconditional jump, like here there is no problem, because we know that if it is after this it gets this jump L2 instruction. So, after this one has been executed, so jump L2, so it should fetch from this address. But anyway, still you need to have that intelligence, that decode stage when this instruction is this instruction actually when say this instruction is in the execute phase, then this jump L2 instruction is in the decode phase. So, at that point I do not know what is the next instruction to fetch. So, the next instruction should be in the fetch stage. So, if I number this instruction 1, 2 and 3, then when this instruction 1 is in execute stage, the instruction 2 is in the decode stage, and instruction 3 should be in the fetch stage. But at this point I do not know what is the next instruction. So, if this because these instructions meaning will be clear only when we come to the execute phase. Okay. So, until and unless this instruction 2 comes to the execute phase, I do not know what is the next instruction. So, that way there is a problem. So, whenever you have got branch instructions, so it creates difficulty, because we have got this the pipeline has to be stalled in between. Now, what this ARM people have done is that they do it like this. So, we have got this compare instruction. So, compare R1 comma R2. So, that is there. Then after that it will be putting these instructions like this. So, it is called GT add R3, R4, R5, and we also have, after that we put LE sub R3, R4, R5. Fine. So, what is happening is that, so first it will be compared, then the next instruction when it goes to execute phase, so it will check whether the greater than flag is set or not. So, if the greater than flag is set, then only this addition will be done, otherwise it is same as the NOP, okay, no operation. Then the next instruction will come into execution, and depending upon the condition, if the less or equal condition is true, then only this this subtraction will take place. So, you see now you do not have to stall the pipeline. So, you can continue executing the instructions. knowing that this prefix part that we have, this conditional code that we are putting before the instruction. So, that will take care of this type of problems. Okay. So, this pipeline stalls will be much less in case of this conditional execution. With the availability of conditional execution, this pipeline stalls will be less. So, that is the thing. The last point that we have here in this slide is that it is the arithmetic operations may or may not affect the status bits. So, normally we have seen that in other processors this arithmetic operation they affect the status bits. So, that carry overflows, the PSW bits are affected, but here we have got two variants of every instruction, like add instruction it has got two variant, as we will see later. One is add, which will be affecting the status flags as well. Then there is another variant add S. So, this add instruction will not affect the status flag, but add S instruction, so it will affect the status flag. And this is useful because as soon as you have got conditional branching, so there may be difficulty, because you can say conditional branching. So, with that we just if you look in the previous instruction, compare R1 comma R2, then GT add R3 R4 R5. Now, if this instruction is allowed to affect the status flag, then when I am writing like LE sub, okay, R3 R4 R5. So, what I want is this flag that I want to check. So, this should be the effect of this comparison and not this addition. Okay. So, in other processors you know that whenever some arithmetic logic operation is done, the status flags will be set. So, as a result this GTA add instruction, so it will be setting this status flags as well, but we do not want that. We do not want the status flag to be set by the GT add instruction. So, this is ensured by putting two variant of this add instruction. So, we will see one is add, another is add S. So, if you say add S, then the status flags will be affected. If you do not say add S, then the status flags will not be affected. So, we have got two variants, add and add S. So, this way we can have different features of so many improved features that have been incorporated into the ARM processor.